Welcome DIKWP, 小工 aboard. Your learning journey starts now. Ever felt like some truths are just out of reach? Like there's a secret your logic system can't quite grasp? That's the vibe of Gödel's incompleteness theorems. Now, meet DIKWP, data, information, knowledge, wisdom, purpose. It's a model for how we think, layer by layer. The juicy bit? How does high-level knowledge K actually translate down to the patterns of information I? And guess what? It turns out, something gets lost in translation. Big time. So, let's break down this DIKWP thing. Think of it like peeling an onion. First, you've got raw data, just facts, no meaning. Then, you find information, patterns emerge, like seeing that 3 is bigger than 2. Next up, knowledge. This is where things get structured, rules, theories, like axioms or fancy graphs. Now, here's the kicker. When you go from knowledge back down to information, it's like compressing a movie into a single frame. You lose details. The paper calls this semantic compression. Mathematically, information is basically data plus context. I equals angle d comma phi angle. Simple, right? But this compression is key. Okay, here comes the main event. Gödel's theorem in the DIKWP world. Remember those true but unprovable statements? The famous Gödel sentence G. It's a perfect example. From the knowledge perspective, G is true. But try to prove it using the rules of the information layer? Impossible. Why? Because mapping K to I involves that semantic compression we talked about. The rich, self-reflective meaning of G gets squashed when trying to represent it as simple information patterns. It's like trying to describe the feeling of love with just chemical equations. You miss the point. This creates a fundamental tension, a gap between what knowledge holds and what information can derive. This leads to a big problem: non-closure. The system can't fully contain itself. When you try to map everything from knowledge down to information, stuff falls through the cracks. What causes this? Well, that semantic compression always loses some nuance. Then there's self-reference, like the Gödel sentence itself, creating loops the information layer can't untangle. And get this, Yucong Duan talks about a consciousness bug theory. Basically, our own minds, and maybe AI, have inherent limitations. We can't achieve absolute completeness. This isn't necessarily a flaw. It's a fundamental aspect of how meaning works across these layers. It explains why AI sometimes hallucinates or struggles with paradoxes. So, what does this mess look like in the real world? Knowledge graphs built without proper semantic constraints can end up contradictory. Think about AI chatbots making stuff up. That's often because they're operating purely on statistical patterns, the information layer, without a solid grounding in explicit knowledge, the knowledge layer. The solution: DIKWP offers a path towards white box AI. By explicitly building those semantic layers, connecting data to knowledge, we can create systems that aren't just smart, but also explainable and trustworthy. It's about giving machines a better sense of meaning. Ultimately, this DIKWP framework isn't just academic navel-gazing. It's a powerful tool, bridging the gap between pure logic and practical AI. It even gives us a blueprint for thinking about artificial consciousness. So, next time you encounter a puzzle that seems unsolvable, remember, it might just be a beautiful illustration of the inherent tension between knowing and understanding. The quest for completeness is ongoing, and perhaps wonderfully incomplete. Thanks for tuning in.